Hi, everyone. My name is Nicholas Lane. I'm a professor at the University of Cambridge, and this is the introductory course that we offer for free to our Deep Neural Networks course taught by myself and Philip. Uh, Thank you all for coming today. I'm going to start by sharing our slides, and we can begin today's session. But again, I just want to say thanks for coming, and it's wonderful to be here. And I believe now you should be able to see the slides. As I mentioned, this is the introduction. It's going to be around 30 to 40 minutes. I'm going to talk about some of the preliminaries that underpin deep learning and sort of get in front of some of the basics that can act as a foundation for when the course starts in earnest in future weeks that we will build on top of. But before I begin, let's discuss a little bit about the Cambridge AI Academy, for which I'm a member and teach this course within. And so the AI Academy has been constructed by faculty largely across the UK and some of the folks in Europe. And where our ambition is to provide a new avenue for largely online learning that's accessible to anyone in the world to experience, and where the teaching is really, with this important term, faculty driven. So we're designing the courses. There's a number of us involved, as you'll see in the next slide. We're designing courses that we really enjoyed and that we really enjoy to teach, and that we think is really important information to learn. And we get to customize the course just as how we like it. Our involvement in the AI Academy is such that we're doing it on an individual basis. So while all of us are professors with home institutions, so myself at the University of Cambridge, but we have others based in Warwick, based in Edinburgh, and so forth. But we're teaching these courses as individuals, and so they're not associated with the university itself, but we aim to provide the same level of standards that we also provide when we teach for our university. So these are courses constructed purely for the AI Academy, but we want to hit the same standards of courses that we deliver within our home institutions. If you look around the course catalog, you'll see a diverse set of machine learning based courses. This one is about deep learning. You'll see others to do with machine learning systems, graph neural networks, finance and machine learning, robotics, mobile health. So a wide spectrum of machine learning impacted topics available for you to participate within. And then finally, this point is that we only wanted to bring together folks from highly respected institutions within the UK and EU. So that's enough about the sort of the underpinnings of the AI Academy. Let's talk about those involved. Here we see we currently have 7 different academic members. We have 3 of us are based in the University of Cambridge, which is why we call ourselves the Cambridge AI Academy. It's a geographic name. We also have professors from Edinburgh, so it's people like Chris Liu. We have Hong Kai Wen from Warwick. We see here we have a couple from the greater sort of Europe, the continental Europe, including Tituan. He is based in Avion. He's associate professor there. And we have Thomas Love. He's an associate professor based in Amsterdam, focusing on finance. So you can see it's a strong mix of people teaching the courses that they love, doing it online, so anyone can really enjoy and benefit from them. Let me tell you a bit about myself. I'm a professor here at the University of Cambridge. I'm a professor of machine learning systems. I have actually it says 8 years there. I have 10 years of industry experience. And I've worked at Microsoft, Nokia, and Samsung. So I've spent a lot of time in industry research labs. I've also spent a lot of my career inside universities. So I was at UCL before moving to Oxford, and and then subsequently moving to Cambridge, where I'm based. And so, so it's a pleasure to teach you all and to sort of dive into the underpinnings of deep learning. And so in this summary lecture that I'll be presenting today, we're going to sort of really briefly go over some of the core topics that provide you sort of a foundational set of learnings that we can then build on in subsequent weeks of the Deep Neural Networks course if you choose to take it. So an introduction is going to start off sort of slow, talking about sort of why is deep learning a big deal? We see it everywhere. Why is that the case? Talk about one of the core ideas, perhaps the core idea within this paradigm, before moving on in part 2 of the lecture, talking about some of the history of deep learning and some of the major events that have happened along the way, at least from our sort of subjective opinion. So with that, let's begin. Why is deep learning a big deal? Well, it's interesting. If you look in terms of interest and growth and participation, deep learning has really been a rocket ship. So these two figures we see here on the left-hand side is NeurIPS in terms of registrations between 2002 and 2017. You can see this nice trend line that existed for many, many years in that period that sort of roughly, they're roughly related to one another. There's no big outlier there. And then you can see this unusual blue line. That's the most recent year of this figure, 2017, where you can see that registrations have just gone through the roof. So, the types of behavior and registrations to this premier machine learning conference is unprecedented. And that's back in 2017. This trend is even further persisted. And so while in the early days, such as in the 2000s, you might have had 2,000 people attending. These days, you get sort of maximum capacity where it's sold out well ahead of the registration deadline, which is completely atypical for a computer science venue. And then there's a sort of funny extrapolation on the right-hand side saying that, oh, well, if the rate of growth that we currently see in, let's just say, NeurIPS registrations continues under its current projections, it won't be that long until the number of people registering for NeurIPS will be beyond that of the total world population. So of course it was a joke, but it's really underlining the rapid expansion of interest and activity of folks in deep learning primarily. So it's no hyperbole to say that deep learning has sort of become a big deal and captures the imagination of everyone. The question is that warranted? Many people would say that it's a bit overblown. They would question perhaps if they see some fundamental changes in the algorithms being used. They might question whether how much theoretical underpinnings are there within this area. I don't subscribe to any of those views. And in my opinion, although it has been a dramatic rise, and although it has been an explosion and to some degree a dilution of expertise given this expansion, I think the activity and the amount of interest is warranted given what it's enabled. And so it wasn't that long ago when, for many types of tasks of interest to machine learning researchers, be it image classification, be it machine translation, audio understanding, and so on. I'm just looking at that list on the left-hand side of the figure. It wasn't so long ago that each of them had bespoke types of features, types of models that were relatively different between the domains, particularly when you looked at state-of-the-art results in terms of models. And what's happened more recently is this trend where deep learning as an approach, as a paradigm, has slowly, one by one, from domain to domain, replaced all of these. And that's a dramatic thing. Furthermore, some of the accuracies that are now enabled by the adoption of deep learning principles in these domains have led to models that are appreciably more accurate than was ever seen before. And so in areas where we saw accuracy and the ability of these models starting to plateau, things like speech recognition and image classification and so forth, we have seen significant leaps in accuracy that have translated into real world impact. And so products such as Alexa would not exist without deep learning and the accuracy to which noisy speech recognition and a variety of other modeling tasks were able to lift to. You couldn't have an Alexa with the prior methods, the non-deep learning methods, because they were just too inaccurate. And so that's just one example of literally products that are used by millions of people that would not be feasible, that would not even function without deep learning being applied and lifting those accuracies. And then the list goes on, particularly in the mobile space. Image classification that we kind of almost take for granted for now on phones. They can do things like recognize an object, enabling things like such as searching for objects within your local photo history. You can right now, you can grab any phone, you can search for a cat in its photo library, and it'll find images of cats. And that would be literally impossible without deep learning. You can do things like in latest smartphones, I saw a feature where you could, if there's a piece of text on something you can see in the image, you can actually cut and paste that text now. And what that function is doing is doing quite high levels of OCR to recognize the text that exists in the image, understand what that text is, understand, okay, this is a visual representation of O and A and C that would underpin you being able to do copy and paste. And so that's a simple feature, but that feature would never exist without the levels of accuracy that we can extract from these fields adopting deep learning. And so there are many reasons that the list can go on as to why I believe deep learning not only is a big deal, but that reputation is actually justified. Let's talk about one of perhaps the key principles in deep learning in terms of how does it differ from conventional machine learning, pre-deep learning era. And the key idea is that instead of having a situation where you have researchers, engineers, experts in the field design algorithms that extract features that are relevant for doing a particular task. So you can imagine the case of recognizing an image, you might design a series of feature extracting algorithms that would do things such as recognizing color patterns, edges, shapes. Instead of having that in the area of deep learning, what happens is that we have these functions learned from data. And so the big shift in deep learning is a shift away from features that act as inputs to classifiers. Instead of having these features be designed by hand and being fairly complicated things that are then passed on to relatively simple classifiers, we have an approach whereby the classification and the feature extractor has merged, and those feature extractions are learned from data alone, depending, and that definition alone can be subjective based on a few factors. But at a high level, the features are learned from the data, and then these features are fed. These features are integrated within the model inside its design. And that's the big paradigm shift. We no longer need to have people designing by hand features. And then so what that means is that the effectiveness of a classifier is not limited by an individual person coming up with a clever idea to extract a useful piece of information that's fed inside a classifier. It's limited by our ability to feed in more data into a model, or our ability to scale up an architecture neural architecture larger and larger to provide more capacity for learning to occur within that model design. So let's expand upon this a bit more carefully and unpack some of the things I was just talking about. In terms of machine learning, when you are relying on handcrafted features, this process looks something like this. In the case of an image, you would provide the raw inputs, in this case, images, to a box that we're calling here feature representation. You can think of this as a collection of individual algorithms that are each extracting a useful piece of information that allows us to recognize or perform the task at hand. So in the case of cars, you could have an individual algorithm that's recognizing a wheel. You could have an individual algorithm recognizing colors. You could have an algorithm that's looking at sort of general shapes. You could, in this case, let's imagine the task is recognizing cars specifically. And so you could have very specific types of feature extracting algorithms that are applied to the raw input that collectively allow us to extract information that when brought together, allow us to recognize if it's a car or not, or what type of car it happens to be. And then if you have very powerful feature representations that are a collection of features, you can have relatively simple learning algorithms because the information is right there. If you have very strong pieces of information, making the decision actually becomes relatively simple. And so, again, expanding this out, what is a feature extractor really trying to do? Well, it's dealing with raw input. So this, of course, is going to be some sort of digital representation of this, in this case, an analog signal. And by having powerful handcrafted features that they're powerful because they're designed by humans, that each focus at different types of factors. So let's imagine that we're differentiating cars, like we're telling two cars between each other, two models of cars, by the shape and the color and so forth, attributes of its wheel hub. And so the aim of a feature extractor that's focused on this wheel hub is that given different images of these hubs, the output of the classifier would be different, corresponding to variations and attributes of that wheel hub. So maybe it's counting the number of holes in it. Maybe it's talking about how reflective it is and so forth. And so no matter what the view of a particular wheel hub is presented to the algorithm, the useful piece of information that it's really working with should remain constant. So if the design of the feature is to react to the number of little holes that you see next to the wheel, its ability to determine that information should be constant or just as effective, no matter how you rotate or move or the lighting of the image. And if that information is preserved independent of noise and variations in the input, then that's a good feature extractor, because then the classifier can rely on that information being present. The challenge in building strong features is something along the lines of what I was just describing. It's not easy to do what I just described, to provide a design of a feature that's going to be consistent, consistently producing the same type of semantics, regardless of the input. And that's because the input to the model, or the input even to any computer, for these types of real world objects and context and information is just a series of digits. And so you see any image, we might think of it as we think of these things such as images, and we obviously as humans start to immediately extract out useful pieces of information. But to a computer, all an image is a collection of pixels. And so of course the actual pixels of a cat are going to change dramatically as the lighting changes, as the angle of the image changes, under many degrees of freedom, because there's no semantic meaning in that input. And so as I move the camera, let's take one example. If I move the camera around the cat, the pixels are going to change, even though the entity of the cat intrinsically has not changed at all. And so you could have two images taken of a cat in this case, and the pixel representations could be dramatically different. And then the objective of a feature extractor would be that even though the inputs are radically different, because they are of still the same semantic entity, the outputs will be invariant. And so if, for example, the feature extractor is extracting how many legs does the animal have, regardless of what the view of the animal is and the angle and so forth, with this particular cat, it would consistently be saying 4. That's one challenge. The other challenge is just sheer complexity. We talked about different types of how do you fill the gap between the inputs that are varying based on a variety of different types of situations and the actual semantics of the image. Another challenge is that one particular class, say a cat, can have a variety of different forms that also look completely different to each other. There is within class diversity. So again, this has nothing to do with the image input changing and the angle and the lighting and so forth, but just that the diversity of the entity itself can change dramatically. You can have, and that's being illustrated on the bottom right, but you can also have variations in how the cat looks. There's deformations. Cats come in different shapes and sizes. There's also complexity to do with not intra-class variety, but just that the background can be very confusing. It's hard to know where the edges of it are. It can be occluded. Even the image I showed before, I mentioned the legs before, but you couldn't actually see them all in one in that one shot. So that's another challenge to building features. And so to overcome this sort of challenges took tremendous effort. And so pre-deep learning, people really put a lot of intellectual energy into designing better and better features that could handle these problems. So there are a long list of famous examples. One of the ones shown here is SIFT. So this is a particular type of feature that was applied to image, where the objective was that no matter how you rotate the image, if the image was the same, it would still have the same ability to recognize the same visual characteristics. And so you see two images of the stop sign, very different. The input, you can imagine what the pixels are completely different. And yet the SIFT algorithm is able to still pick out the same landmarks between the two. And so this sounds great. If you have clever ideas that are invariant to the complexity of the world, you can still build powerful classifiers. And we did that for quite a long time. But there's a number of problems that come intrinsically along with this approach of handcrafted features. And so one of those is the fact that you tend to end up with features that are completely application specific. So not only do you have to have a clever idea or a number of clever ideas to extract useful piece of information to deal with all this complexity from the real world, you have to do it time and time and time again when you go into different application domains. The features that work for recognizing an object are not going to work when you want to recognize words. They're not going to work when you want to be able to interpret text. So for each of these domains, and then increasingly for each of these different tasks, we had to come up with unique, powerful ideas to perform the task well. And then you would actually end up having very different types of classification designs. And that's what this figure is showing you here. We have 3 very common paradigms of machine learning, and there was little to no a sharing of features, of course, and even the classifiers that would be effective within them also had a lot of variations. And so as a powerful alternative, deep learning represents just a dramatic shift to a reusable approach that can be where we have the classification and feature extraction represented by an architecture that's really doing a series of transformations from layer to layer and learning what those transformations should be based on the data itself and the task you're trying to perform. And so if you present the same architecture with one task, recognizing cars, it would learn a certain series of features. And then if you present it with doing another task, such as recognizing a word being spoken by voice, it would learn a completely different set of features. And that was a powerful way to work within. The other types of benefits that we saw from deep learning architectures and this idea of learning a hierarchy of transformations is that we saw examples whereby this architecture, this approach, was able to learn from scratch initial features, early layers that did low-level feature extraction that would then build on each other. And so you would have low-level feature extraction at the start, and these features would then build on themselves to produce higher and higher levels of concepts. And so this was a dramatic sort of improvement in styles of learning. It's a feature that we would, it's a capability we see in other entities that we'd like to mimic. And so as an example of this, and if we take an image-based task, if you look at the transformations that were being learnt, what you saw was early layers that were recognizing things that appeared to do edge detection type of routines. Then the intermediate layers might, for example, recognizing coarse shapes that corresponded to sort of intermediate representations, things like you might go from edges to tires to to whole body shapes of cars at the end, where these stackable layers are learning on top of each other and building on the information of the earlier layers, and doing all of this through data, and then all with the aspiration to do it with a common set of algorithms. And so it took time to be able to reduce the differences between what you needed to do from different domains. But the direction of travel was that the architectures had a lot of reuse across tasks. The learning approaches had a lot of reuse across tasks. And so we're able to at least apply the same principle again and again and again. And importantly, this went along with the observation that these methods were able to beat anything else that we could come up with. And so this alternative was really important. This sort of unpacks what I was just saying before. Again, the basic principle of representation learning is having this sort of configurable set of layers of transformation as defined by neural architecture that defines a series of parameters that can be learned. And then we would have this property of trainable feature extractors that not only learn from the data, but that can also learn and adapt on the information extracted from the earlier layer. And so they could build more and more complex, higher level abstractions that can be used. And this was a giant breakthrough. This type of learning hadn't been seen before, certainly not when applied to complicated tasks that were sort of really the mainstream tasks of interest for machine learning to try to perform well, things like face detection and so forth. And yet deep learning showed promise and eventually has been able to perform these things in the way I'm describing them. And so here we have an illustration of doing representation learning when you're recognizing a face. And you can see the modularity and the reuse in the illustration here that I've been describing. So let's now take a bit of a tour along the history of deep learning. At least we've cherry-picked a few of the sort of important milestones that got us to some of the successes that I was just describing. And what I want to start with is some of the early days of deep learning were actually perhaps much earlier than you suspect. There's this common conception that deep learning is a common, more recent explosion of success, but its underpinnings definitely date back to a long time earlier. And so there are different things, different breakthroughs, different results that we could point to. But what I want to start with is pointing to the 1960s, late 50s work by Rosenblatt at Cornell, when he and his collaborators invented the perceptron, that when we study later in the class, you realize has many of the core principles in terms of neural architecture and so forth that we see even in modern architectures. So the idea was, what I want to point out is that even back in those days, in those early days, people were very excited about what could be possible. And to a large extent, there's a lot of overexcitement in what would be accomplished in the near term. And so something you hear commonly is that, oh, there's a lot of hype associated with deep learning these days. And my point would be that there's always been a lot of hype associated with this technology. And we can see here, for example, if you look on the right-hand side of this slide, you see an article from the New York Times from 1958 talking about Rosenblatt's perceptron, and it discusses how within the next year they expect, quote, it says, the Navy said the perceptron would be the first non-living mechanism capable of receiving, recognizing, and identifying its surroundings without any human training or control. So that's what was written in 1958, and it's what they expected to be possible in short time. And you can see, even today, we're nowhere near achieving, we're only approaching some of that type of capability. So from Rosenblatt's perceptron, which was a single layer, nonlinear model that later in future lectures we'll see just how important that type of capacity and type of design is towards performing deep learning. There was a big explosion of interest. People had high aspirations, but in the 1960s, it was proved that perceptrons of this kind could only learn linearly separable functions. And so that severely limited the scope of what they could learn. And so because of this, there was a rapid decline in interest from that point, because people realized that it was far more limited than they first realized. And things stayed like that until later in the 70s and 80s, when backpropagation was invented, that enabled us to move from single layer perceptron models to multi-layer models that didn't have such severe limitations. And so that increased interest again. People saw backpropagation was going to be a big door opener. But deep learning didn't take off at that point. And they just couldn't find a way to use backpropagation effectively to learn multiple hidden layers, and importantly, perform the tasks of interest, things like object recognition and so on, at a level that could outperform alternatives. And so while there was still a lot of interest in these approaches, the majority of attention and the vast majority of work focused on models that had complex features built by hand, that used fast classifications on top of those heavy features to perform tasks. And so all learning looked like that for most tasks of interest. And so there was a series of scientists that persisted with deep learning style methods. Of course, names that be very familiar to you, such as Jan LeCun, Jeff Hinton, Joshua Bengio, being among the most prominent and heavily contributing of them, that slowly made inroads trying to understand how this type of paradigm could eventually succeed. And arguably, the inflection point in this process where deep learning style methods were much maligned in relation to these other approaches, these other SVM with heavy features style approaches. The inflection point came in 2012, where we had what is known in the community as the ImageNet moment. And so what this refers to is at that time, at that year, roughly speaking, there was this intersection of three main ingredients that enabled deep learning to start to succeed. And they are commonly ascribed to being: one, the advent and availability of large-scale data. And so we had internet-based data such as YouTube, Facebook with lots of images, YouTube with lots of videos, Walmart with lots of customer data. So these are examples of the availability of large-scale data that could be used with these deep learning models was ingredient number one. Ingredient number two was that we had to have enough compute and enough cost-effective compute to train neural architectures of a sufficient size that they would work well enough. And finally, three, so we had them with GPUs. And finally, three, we had to have some key breakthroughs of various kinds in terms of the methods. And so there was a lot of work that built on the perceptron and similar ideas, but there's a lot of other types of methods related to how do we train these models, back propagation and variations that came after it, architectural variations such as LSTMs and other types of designs that enabled us to effectively create capacity in these networks. And so it's the intersection and the arrival of all of these three things at once that unleashed the floodgates of the types of results that we saw from roughly 2012 onwards. And people often point to one particular paper as being strongly representative of this sort of inflection. And then in fact, this is why it's named ImageNet moment, because it was this particular paper from Hinton that presented a method of a CNN architecture that was able to win the ImageNet challenge. And so they presented a design of a CNN that was able to beat everything else in this competition. ImageNet is a challenge that sort of came about roughly in the same time period. The aim was to create a data set that was much larger than the ones that were commonly used, and so that models could be trained in more realistic settings, more challenging circumstances that more closely corresponded to real-world tasks. And so this competition was run year on year, and for the initial few years, the winners, the best models that were invented anywhere in the world, were based on heavy features and simple classifiers. But in 2012, that was the first time that deep learning started to win this competition. And so the winner that year was this architecture called AlexNet, named after Alex Krzyzewski, the first author in the prior paper we just described, where there was a dramatic reduction in the error. And that's what you're seeing on the right-hand side. This figure is the amount of error in the ImageNet data set. Blue are techniques, methods that do or not use deep learning, and purple are those that do. And so from 2012 onwards, not only was there a big jump in the accuracy of ImageNet classification, but from that point moving forward, the whole world changed to using deep learning. And you can see by 2015, the levels of error that were being observed on this task were comparable to those of humans. And so there's a lot of asterisks that you need to attach with that result. So of course, humans were still able to do far better reasoning and recognition than a machine. But in the context of this one particular task and the way that it was defined and the classes that it required recognition of, humans were performing the same as machines, which was certainly very interesting result. from 2012 forward, building on the success and this level of interest, you had this snowballing effect of people looking at how deep learning principles could be applied across a whole range of tasks. There was inventions of new types of architectures, new ways of doing the optimization, alternative areas to apply it to, such as performing deep reinforcement learning, where the neural network would act at the front to learn features of a conventional reinforcement learning system. But then we saw that it could generalize, the same principles could generalize across a wide variety of, in this case, games, and outperform humans. And so there's a snowballing of result after result from 2012 moving forward, where, for example, 2015, people broke through this barrier of having 10 or 12 or 8 layers into the hundreds through a couple of relatively simple but key, absolutely critical methods. And so if we fast forward all the way to more recent times, architectures have been invented, such as transformers, that are now transforming, if you don't mind me using the word, the way that domains like NLP are now being done. And so just to conclude here, this thought, we now are at a point with deep learning that it really dominates all forms of machine learning for the most part. And all of the practical tasks that people care about are being performed using deep learning principles. So a natural question would be, well, what does the future hold? And for many people, the future holds more of the same. I also would agree that a lot of resources, a lot of progress still remains to be made simply by providing more data and larger architectures as a means to get better and better at a wide variety of tasks. And so to illustrate this viewpoint, we are using here this kind of clever, funny cartoon about we have a very sophisticated statistically trained scientist. He's talking about how you should approach the construction and the improvement of a particular model design, really using very sophisticated ideas. And then below we have sort of a joking representation of a deep learning practitioner who gets even better results by just stacking more and more layers on top of each other and adding more and more data to the mix and getting more and more results. And so certainly that is one next step that's bound to happen, and I think will still bear a lot of fruit. But there's much more to it than that. And so if I had to think about what else the future may hold beyond just that, I would say that when you think about what's next, you really need to think carefully about your model design and what is it that you really need to succeed. We need to think about models that can use a wide range of data that are easy to parallelize, meaning they're scalable, that are expressive, that are more expressive than the ones we have today, that are able to consume, I said, wide range of the data, that are able to consume maybe different modalities in combination. Models that are parallelizable, meaning they're scalable, meaning that they're fast to train. Models that are expressible, where they have lots of interesting new novel forms of capacity put inside them. And then what's fascinating about that is the same sort of pillars that gave rise to the ImageNet moment originally. And so it's an interesting kind of connection that can be drawn. So that concludes more or less what is a preview of the style of learning that you'll experience from the Neural Networks course at the AI Academy. It's a 6-week program. Upon recording this lecture, our next particular iteration is going to start on November 4th. If you want to join that class, let us know. In total, the 6-week program includes 30 hours of content. There's 12 hours of actual lectures of the type that you've been just seeing, as well as 18 TA seminars where you get sort of more directed, closer help. And then we think about the core learning objectives from this class. I think there are three key ones. You learn what DNNs are, both from a practical and theoretical viewpoint. You would understand how do they actually learn, are they trained, and how this can be accelerated. And then finally, what are some realistic hands-on applications of deep learning? Just noticed a typo there. Just fix that. And then finally, the things that you'll learn, that you'll earn, well, earn is a bit of a strange word, but those outcomes that will be achieved would be those who successfully complete the course can have a letter of recommendation written by myself to describe how well they did the course, how much did they learn. It can be used for anything that you'd like. It will faithfully detail your performance in this class. And second, by doing this class, you can build up a portfolio of programming and hands-on exercises. And so then that can be useful when you start to apply for jobs, you're looking for your next step, because you can refer them to this portfolio, these examples of code that you've written and things that you've done during the hands-on components of this course to evidence your ability to do machine learning tasks. So, and finally, if you're interested in this, if you've liked this lecture and you want to see more of it, where we dive into the real technical and interesting information, please go to our website. You can book here, or otherwise feel free to contact us through this website to ask any questions about the course itself. So with that, let me just stop sharing, pause sharing. And I just want to say thank you again very much for attending today. It's wonderful to see so many of you there. I'm also recording this lecture so you can watch it later on and decide for yourself whether it's something you're interested in. So again, thank you for coming and spending your time with us. I wish you the best and take care. Bye for now.